So we're at the point in this section where you've sort of already learned the most important stuff, but there's some little details that I have to pick up to make sure that you know everything that you need to know. And what we're going to get at in this video is more of an observation than me really teaching you anything new. And that observation is, up here, when I asked you for an output, when I told you the input and asked you for the output, you may have noticed that in every single one of these cases, there was only one specific answer. However, down here, when I gave you the output and I asked you for the input, sometimes, not all the time, but sometimes, there was more than one answer. And that wasn't specific to when a function was given in terms of it's an equation. That also happened when we talked about the graph. If I ask you for the output that corresponds with 4, there's only one answer. The answer is the number 5. But if I ask you for the inputs that correspond with an output of 5, there's two different answers. A 0 and a 4 both work. We even saw that when we talked about tables, although I don't think I explicitly called it out. Note that when I put -1 in or +1 in, the number 2 comes out either way. Another way of saying that is if I asked you to find the inputs that correspond with an output of 2, you'd have two different answers. But if I ask you for the output that corresponds with the given input, like the input 2, well, then you're only going to have one answer. From the examples that we've done so far, you might come up with this observation. And that observation is that there are often more than one inputs that correspond with a given output. And maybe parenthetically, I'll add that there's never more than one output for a given input. In terms of our flow chart, it's totally fine to take two different inputs, I don't know, 1 and 5 maybe, and in either case have the same output come out, maybe the number 2, sure. But it doesn't make any sense to have some number like the number 3 go into a machine and have the number 8 come out of the machine if some other time when you put the number 3 into the machine, a different number like, I don't know, 10 comes out. You can't have two different outputs for a given input, but you can have two different inputs for a given output. And you're like, yeah, whatever, who cares? Well, that's more important than you might think. To emphasize the importance of this fact, I'm going to give it a fancy name. I'm going to call this the defining characteristic of a function. We've been talking about these mathematical machines really abstractly, but there's actually some rules that they have to follow. And the most important rule that a machine has to follow if it wants to be classified as a function, this fancy thing, is it has to be what's called well-defined, meaning that we can't put a 3 in and have an 8 come out sometimes, but have a 10 come out some other times. That wouldn't make any sense. The machine has to do the same thing to 3s, so when I put a 3 in, there has to be only one output for that 3. I can't have two different outputs for it. How would that possibly happen? I don't know. What if I came up with something like f of x equals x squared plus 3x plus or minus 5, right? If I wrote this down here, and you tried to put in, I don't know, 1 maybe, and you're like, well, then I guess it'd be 1 squared plus 3 times 1 plus or minus 5. So I'd get 1 plus 3 plus or minus 5. So I would get, let's see, 1 plus 3 plus 5 is 9, or 1 plus 3 minus 5 would be -1. So I guess for this input of 1, there's two different outputs, 9 and -1. Well, sure, you can write this equation, but this would not be a function because I'd be violating this defining characteristic. I'd have one input, the number 1, that leads to two different outputs. So here's an example of something that would not be a function. I don't even like leaving this in my notes because I'm kind of writing it in function notation, which almost implies that it is a function. But I'm going to leave it here just because hopefully it helps you understand what does not work. This is a function. This is not a function. Here's an example of something that's bad. What you'll see in this class is pretty much everything that we learn, we're going to look at in two different lenses. We're going to look at it in like an algebraic lens, so when we define a function this way, and we're also going to look at it in a geometric lens, like when we define a function in terms of its graph. An interesting question is, I can give you a graph and ask you the question, does that graph represent a function? Here's an example of a graph that does not represent a function. Why does this graph not represent a function? Well, let me pick on two specific points. This point right here and this point right here. This point right here has an x-coordinate of 5 and a y-coordinate of 4. This point down here has an x-coordinate of 5 and a y-coordinate of -2. Think about what that's saying. If this thing were a function, I don't know, if we called this thing maybe h, which I'm hesitant to even write this because it's not a function, so I don't like writing it in function notation, but maybe for the purposes of illustration, I'll leave this. If this were a function and it was called h, we would be saying that h of 5 is equal to 4 because this point is on the graph. When I put 5 into the machine, 4 comes out of the machine. But we'd also be saying that h of 5 is equal to negative 2 because of this point. When I put 5 in the machine, negative 2 comes out. That's problematic. I can't have the same input, 5, lead to two different outputs, 4 and negative 2. This is a perfectly fine graph that's shown here. It even has an equation that corresponds with it, but really for our purposes, we can ignore that for now. But this graph does not represent a function, and that's the important takeaway from here. Why does it not represent a function? Well, because it has two different outputs for this input of 5. And you're like, all right, I mean, that's fine if you labeled these two different points, and I guess I could see that h of 5 equals 4 and h of 5 equals negative 2, and that's problematic. But can I generalize that? Like, how would I know if you gave me some other example whether it's a function or not? Well, there's this thing called the vertical line test. Note that because 5, 4 and 5, negative 2 both lie on my graph, I can draw a vertical line, a line that goes straight up and down, that intersects my graph in more than one spot. It intersects it here at 5, 4 and here at 5, negative 2. What the vertical line test says is if you can draw a vertical line that intersects the graph in more than one point, then that graph is not a function. So if I just presented you with this graph in green, maybe you could look at it and ask yourself the question, would it be possible to draw a vertical line that intersects this graph in more than one spot? Yeah, it'd be easy. Most of the vertical lines, that's not the greatest vertical line. Most of the vertical lines that I draw intersect this graph in more than one spot, right? This vertical line intersects here and here. This vertical line intersects here and here. This dotted vertical line that we already drew intersects here and here. It's absolutely possible to draw a vertical line that intersects this graph in more than one spot. To be clear, not all vertical lines are going to intersect this graph in more than one spot. I could draw a vertical line right here that only intersects the graph in one spot. In fact, I could draw a vertical line out here that doesn't intersect the graph at all. But that doesn't matter. The question is not, do all vertical lines intersect the graph in more than one spot? It's, can you draw a line that intersects the graph in more than one point? Can you? Can you do it? Yeah, it's easy. Okay, if you can, the graph is not a function. And the converse of this statement maybe is the most useful one. If you can't draw such a line, if it's not possible to draw a line that intersects the graph in more than one spot, well, then the graph is a function. So if we go back to all of the graphs that we've seen so far, like this guy, it's not possible to draw a vertical line that intersects this graph in more than one spot. Any line you draw is only going to intersect it in one spot. Same idea up here. Draw whatever vertical line you want, it's only going to intersect the graph in one spot. That means that this graph is a function and that this graph is a function, but this graph is not a function. The way I think about it is if you fail the vertical line test, meaning you're able to draw a line that intersects this graph in more than one spot, then the graph's not a function. And as long as you don't fail the vertical line test, well, then your graph is a function. We haven't talked about why it's important that a given input only has one output. I think at this point in the class, I'm just going to ask you to trust me on that. But that is the case, and it'll turn out to be really important. And because it's so important, we want to understand it both from an algebraic point of view and from a geometric point of view, in which case the vertical line test is a helpful way to kind of qualify what's going on.